welcome to Thermochemistry or Thermodynamics. We're going to look at mostly heat transformations in chemistry in terms of enthalpy, heats of reactions, heats of combustion, all those sorts of things. So first we need to define a few of our terms. The first one is temperature, which we use to measure the degree of hotness or coldness of a body. Normally, in terms of kinetic molecular theory, we might talk of temperature in terms of the average kinetic energy of molecules. This really applies mostly to gases, but we do think about the heat in molecules as basically as the average kinetic energy in the molecules in terms of their vibrational, rotational, and translational energy. So the heat that we're actually talking about in chemistry is really a transfer of energy due to temperature differences. The amount of heat energy is transferred is proportional first to the mass and also to the type of substance that's involved. And this results in a definition for heat capacity. So the specific heat capacity that we have is specific to a substance. When you're talking about heat capacity Cg, you're talking about heat required to raise the temperature of 1 unit mass, so Kelvin, a kilogram or a gram, through 1 degree Celsius or Kelvin. It's the same scale, so that works quite well. You can also talk about the molar heat capacity, which is the amount of heat that's required to raise 1 mole of substance instead of 1 gram. And that's much more useful when we're talking about heats of reactions, particularly in chemistry. And the way that we measure these things is using calorimeters, which have an insulated vessel with a solution inside which you measure the temperature. And you might add something to the solution, or you might have a reaction, or you might even just heat it up to find out what happens. And you calculate the temperature difference as a way of measuring the heat in the system. So our first law of thermodynamics in physics is that energy is conserved. In chemistry terms, what that means is that the amount of heat that is gained in a system is equivalent to the amount of heat that's lost. The example we had in class was some cold water that was dropped into a glass which had warm water, and what is the final temperature of the system. So we can look at the energy that was the heat that was gained from the cold water as equivalent to the heat that was lost from the warm water. And we can look at the temperature final minus the initial temperature of the cold water and the temperature initial of the warm water minus the temperature final of the warm water. You have to be careful a little bit with these negative signs. One of the ways to do this is to look at it and say, okay, if heat is gained, then it's positive. If heat is lost, then it's negative. And then you never go wrong. You can also use your delta T and know that on one side it's going to be gained, on one side it's going to be lost. You do have to be careful with those temperature changes though, in case that. For in this case, what we want to do is look at the example and say, okay, we started off at 5 degrees for cold water and a small amount of it, and a large amount of water at 20 degrees. So our final temperature should be closer to 20 degrees than it is to 5 degrees, which is what our answer is. It's always good to double check. So if we use the same example but used ice instead of water, then the energy wouldn't seem to be conserved, but it really is. That's just because some of the energy that is used to change the solid into a liquid. And that energy is called the latent heat of fusion. So it's the energy absorbed per mole of substance when it changes from solid to a liquid at constant temperature. And you can also have the latent heat of vaporization, which is a liquid to a gas. For an example, a similar example to before, we're using ice this time, but it's at 0 degrees, so we don't have to consider the temperature change, just the state change. The heat that is lost by the water is equivalent to the heat that's gained in melting the ice and the heat that's gained in warming the icy water. So we can add in all of those values and work out a final temperature of about 16 degrees, which is not unreasonable. This is easier to see from change of state graph. So if you're given a question where you're not quite sure what you need to include, change of state graph is a fantastic way of doing it. You have a temperature versus time, and every time as you're increasing a solid substance, the temperature does increase until it gets to this plateau. This is where the change of state occurs, so solid turns into a liquid. And in this case, the temperature does not change. The temperature doesn't change to a state change. And that's because all the energy that's supplied is being used to convert a solid into a liquid. And then you heat up your liquid and you get to the heat of vaporization. So in this case, the liquid's been turned into a gas, and all the energy that's applied here is in that state change from a liquid to a gas. We define a heat of reaction as the heat that's released or absorbed when a chemical reaction occurs. So for a particular chemical change, the heat of reaction is dependent on the amount of substance that you use, and also the specific heat capacity of the substance. Now sometimes you're looking at solutions, so you might be using specific heat capacity of water. Sometimes you might be using other systems, like a gas. For example, we've got the specified reactant is nitrogen and hydrogen, which are combined to form ammonia. And the energy for the system is 92 kilojoules. The energy per mole of nitrogen reacted is 92 kilojoules per mole, or minus 92. And that energy is called the heat of reaction. But when it's in kilojoules per mole, we call it enthalpy. So enthalpy really is basically this heat of a reaction. The enthalpy heat can be measured for reactions, but enthalpies are generally calculated theoretically in various ways, which we'll go through, and they can be compared to other reactions because you've got the kilojoules per mole, so you can compare two different reactions as long as you've got enthalpies. The change in enthalpy for a chemical reaction is defined as the heat absorbed per mole of specified reactant or product when the reaction occurs at constant pressure. Constant pressure is important here, but we won't do a lot about pressure until we get to the gas laws, so just make sure you include it in your definition. And it's due to the enthalpy is the net energy that's produced in an exothermic reaction, or the net energy that's required for an endothermic reaction. We'll go along to define what endothermic and exothermic are. But first, where does the energy come from? Most chemical reactions involve making and breaking bonds. Heat is the most common form of energy that's produced, but often you might get ultraviolet light or sound or flames, things like that. The energy that's released or absorbed in these reactions is called the bond dissociation energy. Sometimes we call it the bond energy. And if it's introduced from the surroundings in the form of heat, in this case where chlorine, this gas is turned into two chlorine molecules, then we call it an endothermic reaction. But if it passes from the system into the surroundings, then, such in this case where chlorine molecules are turned into chlorine gas and heat is produced, we'll call it an exothermic reaction. In any exothermic reaction, some of the potential energy that's stored in these bonds is converted into thermal energy, or random kinetic energy, through heat. So the energy is released to the surroundings. And that's really because the reactants add a higher potential energy than the products. And the example we've got here is methane. So this is combustion of methane, which is always an exothermic process. An endothermic process is the opposite. So it's when a reaction absorbs heat from the surroundings. And in this case, it's when the reactants add a lower potential energy than the products. The reaction here is nitrogen and oxygen forming nitrous oxide, which is an endothermic process. Some of the enthalpy diagrams that you often use, remember the previous diagrams were looking at potential energy, and these ones are looking at enthalpy, so it's the enthalpy of change of the reaction. So in this case, we often use the reactants here and the products here. So the reactants are below the products. So we're going to require energy to get to the products, which means it's an endothermic reaction. And your delta H, your change in enthalpy, is positive. For an exothermic reaction, your reactants have a higher enthalpy than the products, and so you're releasing energy, which means you're going to give off heat. But that means that the delta H is going to be negative. So, positive for endothermic, negative for exothermic. If the direction of the reaction is reversed, then the sign of the enthalpy change is also reversed. So, an exothermic in the opposite direction becomes endothermic. The enthalpy change is per mole of specified reactant or product because of this direction issue. So if you had it in one direction, it was exothermic in terms of reactant, then in the opposite direction, it's endothermic in terms of product, so that you have that same direction and the same product. The delta H also depends on the physical state. We'll get on to that when we're talking about it, because you can calculate your enthalpies of reaction based on the physical states and the bonds that are changing. and they all have to be included when you're writing